give rise to an n equals 1 theory in formations. So what I mean is this system base is over it defined as a complex form manifold or as a plane manifold, it's a Bloch form and it's a positive singular. On the face of it, that looks like it must come from a very different algorithm type we've been using. What we've been saying is, what you do is you look at the action on now this 12-dimensional space, and then you vary the fermions and you see what some solution. We don't have a 12-dimensional action here, right? There's no 12-dimensional action in theory. This torus is just a trick for describing the scalar field, essentially. So where does this statement come from? What is this? Well, what we do is we use some dualities. Basically, there's an nature of fields, right? So you relate, because you don't have to do that in case it looks the same as what we do. So what we do is we use some dualities to relate this statement back to somewhere we do our usual analysis of the Killing equation and try to do a solution. So the two dualities we're going to use are the M theory. So this is the 11-dimensional theory on the circle. It's my S duality. The same thing as type 2A string theory. In fact, the type 2A coupling is relatively just the radius of the circle over the string. So if you take this circle, it's usually 11 dimensional space time to be a circle times something. If you take the circle zero size, you go back to weakly coupled 2A string theory. So how do people know this? Well, there's a nice description of this in a paper by Whitman called String Theory in Various Dimensions. What they do, the way they see that this is true, is there's certain states in type 2A string theory which are BPS, where they're protected, so certain quantities are protected against quantum corrections. So what we do is we take those states, you look at the spectrum, and then you take the limit when the coupling goes large. You believe the results still because of this protection. What you see is the clues applying tower, or a reduction of M theory on S1. So there's some duality that relates M theory on S1, which is type 2, where the S1 is 2. There's also T duality, which relates type 2A theory on an S1 to 2B on S1. This is just some geometry variables of Wiltshire. When you do that, the 2B coupling is given by the 2A coupling on the radius of the circle. So the idea to get from M theory is to get M theory to F theory using these dualities. What you do is you just combine the two circles and you make these torus directions. So I'm just going to do it for a square torus, because it's very important to think about chords. So I'm going to say that M theory on square T2 times something is the same as 2B on just that something turns up. So what I'm doing, we're taking these T2s, one direction is this circle, one direction is this circle, and I just shrink the size of the torus to 0. And as I do that, as this direction shrinks, I go to 2A string theory with this coupling. And when I shrink this circle, I go to 2B string theory with this coupling. So the final 2B coupling. Yeah, thank you. Okay, so take the next one to infinity. Thank you. Yeah. So the 2B coupling in this case is 2A coupling L circle of T, which is just here to on S over RT, the ratio of the size of these two circles, but that is the complex structure, at least the imaginary part. It's the imaginary complex structure without torus. So if you take M theory on T2 and you squeeze it down, you get 2B theory on this space. And if you squeeze this torus to 0 size, it's going to come up this way. Where the complex structure of the torus gives this field formula, so that's F theory. Okay, so what do we do now? Well, now we want to amplify, instead of just having a direct product here, we want to amplify some trivial manifold and get down to the four-dimensional theory. So what we do instead is we fiber T2 over M3 times 6 M6. So you take M theory on the T2 vibration over this 6-dimensional manifold times the 3-dimensional manifold, and you do the same set of dualities. And just because if you look at the 6-dimensional manifold, which is like the vibration is trivial, the argument is that they call it the adiabatic approximation, but you can do the same set of dualities, and what you'll get is instead of 2B on, when you take the limit flat space, you get 2B on M6 with this torus, the F theory torus 5 over 1. Okay, so how does all of this help us with supersymmetry? Well, the idea is this. I want to know why this T2 vibration over the 6-dimensional space should be Columbia fourfold. What I do is I look at M theory, 11-dimensional theory, on that Columbia fourfold, amplified down to 3 dimensions. There is an action. There is some way we can do the calculation, and we can work out the theory with a certain amount of supersymmetry again. I can really work this out with the flux side, for example. You can actually do the calculation, work out how much supersymmetry you deserve. But according to duality, we do the same with M theory on the same space. So you use the same techniques, but using dualities to relate the cases, to relate the statement about supersymmetry to a case where you actually have an action. Okay, so finally, that's what I'm going to say about preserving supersymmetry. And we're just going to go on to briefly beat. So today has been quite wordy. We've just been talking about why you're interested in algebraic geometry, where it comes from, how general these techniques to solve the Killing equations are. Tomorrow, we're actually going to go on to start doing some problem calculations. And when we do that, we're going to be working on examples of Columbia threefolds. So I'm just going to introduce the examples of Columbia threefolds we're going to be working on. So that we're ready to talk about vector bundles tomorrow, which is what we're going to do. So how to choose a set of Columbia threefolds to work on? To give examples that are going to be giving you an idea of what the subject as a whole. So it's pretty difficult, but I decided that we're going to, because there again, things I won't do every day, we're going to use a set of Columbia threefolds called completed sections in products of projective space. Now this is a very small, really, it's a very small set of Columbia manifolds. There's only some 7,000 of them. But they have some nice features. One is that it's a big enough set that you see lots of different types of structure in there, which you'll see. Another is that they illustrate the general principles of how you often describe Columbia as this subject. And in particular, the technology that we'll develop to calculate things on these Columbia threefolds directly applies as well to the biggest set of Columbias, the height surfaces and Tauri Cantor spaces. So you can learn a lot by studying these simple cases. There are lots of them to deal with in Tauri, but you learn the techniques that you need to know. And to introduce what these are, it's easiest to give an example. So these are completely classified, the manifolds now, and they're determined by a matrix, written as a matrix, which looks, for example, like 5 cubic. And this matrix defines the Columbia theory. So what do we have here? Well, basic idea of this instruction is that, as you're going to describe your complicated Calabi-Yau manifold and have some calculation control by embedding it in something simple. The simple thing is called the ambient space, and the ambient space here is just going to be a direct product of P2 times P2. And that's what this first column is. So we have an ambient space. And as we were doing today, we're going to describe the variety inside this by the vanishing locus of a homogeneous polynomial in the homogeneous coordinates of the projecting spaces. So we have the vanishing locus of some polynomial, the Calabi-Yau. And this determines what the polynomial is determined by this column. So the idea is that the Calabi-Yau is the vanishing locus of a bicubic polynomial. So the way it works is each time you function, the numbers here give you the degree of the polynomial in homogeneous coordinates of the associated ambient space. So another example would be, if I broke it down, a manifold called Quintic. This is defined by a Quintic polynomial in homogeneous coordinates of P4 where that vanishes. So in general, you can have several products in your ambient space, so this can go on and on. And you have to define the degree of the polynomial in each piece of the ambient space. In general as well, you can have more than one equation. So the Calabi-Yau manifold would be the intersection of two polynomial equations if you start with an ambient space. And if that's the case, so it's more p's here, and there's more one equation, you just have separate columns for each equation. So like I say, there's lots of ways things Calabi-Yau, which we'll see next time, and you can just go through the classical ones. What else do we have here? Well, we have this, and we have this number. What are these? Well, these are the number of harmonic H11 forms, and the number of harmonic 1,2 forms on the manifold. And again, we know how to calculate these next time, so these are H11 and H12. And we're actually going to consider a special type of completed search in Calabi-Yau that has a special property. It's very much linked to its ambient space. It's not. It has extra detail that you can gain about Calabi-Yau living inside the ambient space because of a property called favourability. So as always, there are several different definitions of favourability in physics literature. So I'm going to tell you what I'm using, again, not to be confused. So what I mean by that is that H11 of this manifold is 2. And there is 2 projected spaces. Now I can get one harmonic form of this manifold by restricting essentially the Kähler form of this P2 to the surface. I can get another one by restricting the Kähler form of this P2. But that completely gives me a basis of my harmonic 1 forms on this manifold. So very roughly, favourability means that all harmonic 1 forms descend from the ambient space. We will see when we start writing sequences up what that really means next time. But the thing I want to leave you with is, again, the way you deal with these manifolds is having them embedded inside something simple. The reason that this is a useful property is it's another property of the Calabi-Yau that's directly coming from the ambient space. Okay. So I keep telling you this is the Calabi-Yau, why should you believe me? How do you know that this is the Calabi-Yau manifold? So what we're going to do is we're going to do the really stupid way of figuring out this is the Calabi-Yau manifold today. And I suggest you try it at home. And then tomorrow we'll do the sensible way of proving this is the Calabi-Yau manifold using the algebraic geometry. And then you'll see why algebraic geometry is a good thing, because you'll see how much work it's saving you. I really sold you doing that calculation, didn't I? Okay. So how do we know this is the Calabi-Yau manifold? What is the stupid way of doing this? Okay, what do we need? We need it to be Kähler. Yeah. And we need C1 and TX to be 0. Okay, this is clearly Kähler. I mean, it's a complex submanifold of the Kähler manifold. Just restrict the Kähler form, this is the Kähler manifold, so this one's okay. What about C1 TX? Well, this is the cohomology class of traces with the forms in it, so this is something that basically you need the metric to work out. So you may think, well, there is stuff, I had no idea what flat metric is on this space. We know metrics on P2 times P2 is the Finnish study metric. So we can take the Finnish study metric, we can restrict it to the Calabi-Yau, but that's not the flat metric, that's not the metric that should along it. So how am I going to calculate C1 TX? Well, we're going to use the fact that it doesn't matter, given complex structure, it doesn't matter which metric you calculate this with, it always gives the same answer. So if you take the metric, the Finnish study metric on P2 times P2, restrict it to say the cubic height sets inside P2 times P2. If you then work out the trace of the Cauchy-2 form, you should be able to write that in terms of you can do it, it works. I've actually done it for free, I've done it for the works. So that means that just by knowing about how this surface lives in the ambient space, we'll be able to figure out this Calabi-Yau. We'll find a much better way of doing that tomorrow. It doesn't involve this differential geometry stuff. And that will be helpful. So I'll just say a couple more things. So first of all, we can already see some moduli of the Calabi-Yau, and this will be an important thing for us tomorrow. Or actually, yeah, tomorrow in the third lecture. So we have this defined polynomial, P, which tells us where the Calabi-Yau is in the ambient space. And P is just some terms of coefficients of all the possible polynomials which are cubic in both the coordinates of homogeneous coordinates of both P2s. So schematically, these polynomials are something of form x cubed, y cubed, where x1, x2 is coordinated, where x is homogeneous coordinates of this P2 and y is homogeneous coordinates of this P2. But you can see, we are specifying and giving the Calabi-Yau is the degree to have an active unilateral polynomial. And as I change these coefficients, this guy is going to move around inside the ambient space. But all you need for it to be Calabi-Yau is that the degrees are right. So these are moduli, right? You can change these coefficients. The Calabi-Yau will move and morph and change, but it will still preserve supersymmetry, it will be still be supersymmetric. So these are, in fact, a redundant description of the complex structure moduli. Why are they redundant? Well, again, we'll see this properly tomorrow when we do vector bubbles, and typically we'll return to bubbles this time. But they're redundant because, for example, if you imagine scaling all of these coefficients in the same way, multiplied all by 2, you don't change one to 0 because of the polynomials. So it's clear that the overall scale of the polynomial won't move the Calabi-Yau. You can just put a scale on it, it's not the same solution, P equals 0. So it's clear that while these are a set of moduli theory, that they're a redundant description because they're moduli. And exactly how to get back to the proper description we'll see tomorrow. In fact, this is supposed to be the number of complex structures of the Calabi-Yau. And if you work out the number of bicubic polynomials, you find out there are many, many more. So that's redundant. Okay, last comment I'll make. Here we've been talking about 3 folds, but the same construction of Calabi-Yau we use to construct Calabi-Yau 4 folds to use an F theorem. So let's just try a second look at that. So, the Calabi-Yau 4 folds are not classified with the 4 folds, people say 4 folds are products of projective spaces are not classified yet, but I'm doing this with Alexander Hout two equations now. So 6 minus 2 is 4, so we've got 4. And our two equations are going to be cubic in the first P2, linear in the first P2, and something that doesn't depend on the homogeneous coordinates in the first P2 at all by quadratic remaining two P2s. And the reason I've chosen this one is it has another property which is useful for this ethnic stuff. So there are general conditions for when a Calabi-Yau threefold is elliptically fibred. You can check it. I mean, maybe some people in the audience can correct me here. I don't know the analogous conditions for Calabi-Yau fourfolds. In general, knowing whether it's elliptically fibred, maybe that exists, I don't know. But this Calabi-Yau fourfold is obviously elliptically fibred. So let's just see what that is. So what we have here, well, let's just consider this this equation first. What does this look like? If we don't impose this equation, but just look at the ambient space for this one, what do we have? Well, this equation doesn't depend on P2 at all, the first P2. So we'll just have, we'll call this x space. So x is just going to be P2, this one, times this equation, inside P2 times P2. So this is just some three-dimensional, sorry, it's x, k is just P2 times x. So this is just some variety times P2. P2 is not Calabi-Yau, just some. We're going to direct back to P2. Okay, great. What happens when we impose the second equation? So imagine choosing a point on x. Okay, so choosing values for the homogeneous coordinates here, such that we solve this equation. That will give us a value for this linear piece and a value for this linear piece. And at each point on the base, what we'll get is a cubic equation in the homogeneous coordinates of P2, describing a one-dimensional variety. So we get this sort of cubic in P2 fibered over this base space. Okay, and the cubic in P2 is a torus. So it's got the right genus and it's obviously it's Calabi-Yau. So just by looking at configuration matrices, which is what these matrices are called, in some cases you can see if something's elliptically fibred or not, and then we can do a very theory stuff. Okay, I'm running out of time, so I will just say what we did and then what we're going to do tomorrow. So what we've done today is we haven't really looked at any algebraic geometry at all. What we've done is discussed where does algebraic geometry come from in string theory, and most of the time it comes from trying to solve a Killing-Spinner equation to preserve a certain amount of supersymmetry, even if it's doing that rather indirectly. These supersymmetry transformations can be supersymmetry transformations on branes, they can be supersymmetry transformations on the total space-time, but the same kind of principle tends to work. We saw that in general, if you want to look at most general types of solution that preserve supersymmetries, there is supersymmetry that are not going to be algebraic varieties. So we are specialised hugely to be able to use this technique most of the time. Given that, we better get a really big paper and have a calculate that specialisation. And what we're going to see in the next lecture is exactly what that is. So the next lecture, what we're going to do is and then how to use those next ones to calculate more of that and that's on the game themselves. Yeah, that's all for today. Is there any more questions? So if you did the same analysis in type 2, it would be the same, you'd have two spinners instead of one. But it's basically the same analysis, yes. And that's why it's an interesting thing to use to look at, right? I mean, basically you do the same type of calculation each time. Yeah. Sorry, I think yeah, references. So the two papers I gave for the general argument of why preserving n equals 1 supersymmetry with a Calabi-Yau works, I actually recommend the second volume of Green-Sharp's Witten, and I can look up the page number for you if you're interested, but it's actually quite fun. For the SU3 structure stuff, just for an introduction to it, but also as a way into the literature to see why that is the an interesting thing to look at, I really recommend this reference I did put up in the middle, which was this reference of Nico Boardroom and other people I don't remember, but you can find it on the preprint archive here. They have a lovely introduction where they go through this description. I hope no one in the audience is going to get through. They have this lovely introduction just in words, like I said, but then they have obviously the detailed mathematics written out. For the stuff with the domain wall solutions, which is related, there is this paper by Lucas and Matty, which was the other number I gave. But then for the Calabi-Yau spaces that we've just been talking about, in particular for the technology that we're going to use tomorrow, the bundle technology, I'll give you the references of the stuff to lecture tomorrow, but there is a book by Tristan Hutch, which is called, the Calabi-Yau manifolds, we're going to be able to tell me, I think it's the best physicists of the last time I looked, this book was out of print. I don't know if it's back in print, but you can get second-hand copies on Amazon, that's where I got mine. You got recently? Okay, great. Yes, we don't do what you do. Okay, but this thing describes these kinds of constructions of Calabi-Yau, but also, other constructions based on similar types of technology. There's also a thesis that's useful for bundle stuff, I'll give you that one. Yeah? I was thinking you could have said without string theory, we have that right? Yes. Is there microscopic, I mean, you know that there are vacuum over microscopic, I mean, nowadays people always work yeah, I mean, I think you only know informed field theory on a very restricted number of spaces, right? I mean, you're taking a limit of the string theory first, so I think, yeah, right, and even for the non-Ricci flat metrics on the Calabi-Yau, you get once you get gauge points, arguments that you're still doing the right thing. I don't know the equivalent argument for issue structure for this solution. I don't know the equivalent argument. So there's some work by Adams, which and in fact there's some work by people called Niblin, who's here, so he may be the person to talk to, which tries to do some special cases where you can, of an SU3 structure manifold, where you can write down at least GSM type stuff. And this is mainly based on you make the manifold by being a torus vibration over something. Right? But in general, if you ask me, if I have a general SU3 structure manifold, is that really a vacuum of string theory? I've got no idea. It's a vacuum of low energy theory. I guess that's today. lecture, we looked at what the conditions were to preserve supersymmetry. In particular, we looked at the lowest order and string length expansion of the heterotic string. But the type of thing we were saying applies in general. And we looked at what are the conditions on a manifold, on a solution, such that you preserve a certain amount of supersymmetry. And we saw that in general you get some very difficult to solve set of equations, but if you really specialize further, you get something that can be described as algebraic variety. And I said many times that's going to give us a lot of computational power. So basically last time we didn't know algebraic geometry, and that was because we hadn't finished algebraic geometry lectures yet, right? So now we have, so we can start to think about using algebraic geometry to actually attack some of these problems and actually see some of this power and flame coming out. So to do that, we've got 2 lectures left. So in the first lecture, we're going to talk today about vector bundles over our Calabi-Yau spaces. I introduced this set of Calabi-Yau called complete intersections of products of projective spaces at the end of last time. We're going to start to look at bundles over those Calabi-Yau and actually compute things. And the goal of the lecture, I'm not going to try and prove every little formula I use. Right? There's 2 reasons. One is I don't really have to because our method is such that I think we've proven a lot of the things that we actually need to use anyway. But the other thing is that I don't really want to show you the details of how in this particular computation I go through and I end up with this integer as an answer. What I want to show you is to give you an idea of how you put one of these calculations together. So any one of these little tools, for example, this is called a geometry, any one of these little tools, you can look up very easily in the textbook and see what the proof is. What's difficult to know, as then can be difficult even looking at papers where people are doing calculations like this, is how these tools are put together to actually get an answer. So that's the thing we're going to try to stress. So you may ask, why on earth you care about looking at vector bundles and doing calculations with vector bundles over Calabi-Yau and Calabi-Yau in these cases? And roughly speaking, there are 2 reasons. One is by looking at something called the tangent bundle, you can learn more about the Calabi-Yau itself and how that is involved in the dimensional reduction of your string theory or your high-dimensional theory. And the other reason is that very often you have gauge fields in your string theory setup, and those gauge fields are described as a connection on the vector bundle, and by studying the vector bundle itself you can get very powerful tools for studying essentially gauge field beds in a solution. Okay, so we're going to do this in this lecture. We're going to play around with these sort of abstract techniques in this lecture, and it always looks kind of surprising. So what we're going to do is basically some more sequence chasing. We're just going to watch numbers go through these exact sequences. And it always leaves me with a suspicious feeling when I see something like this. I mean, it's perfectly fine, but as a physicist, someone who's been trained in a certain way, you like to get more into the guts of it to see what's going on. So in the next lecture, what we'll finish up by doing is talking about basically computational techniques, things you can do on the PC to actually manipulate polynomials, because after all, once you turn things into a problem in algebraic geometry, all we're doing is playing polynomial equations, basically. So in the third lecture, we'll go on to do something more concrete. We'll look at some of these polynomial methods, which I will, especially simple, we'll be able to do proofs. And then we'll use that to do one big example of something physical at the end. Okay, so let's start, actually chip 2, which is going to be vector bundles. So how do vector bundles come into our theory? Well, there's several different ways. Let's start with our usual case of the heterotic string, and then we'll talk about generalizations in a minute. So the action I gave you for the heterotic string last time was actually the lowest order in non-expansion string. Let's go to the next order. There's a connected term with some gauge fields. And those gauge fields, it's also important that they're either valued in an E8 times E8 gauge group, or they're valued in SF32. And you can ask, what do I want these gauge fields, what equations do I want these gauge fields to obey if I'm going to look for a solution of my theorem? Now, we chose how to pick a solution for metric and the dilettante range. Well, we chose that solution to preserve a certain amount of supersymmetry. So if that's going to be your justification for choosing a solution for those fields, you better choose your gauge fields in such a way that they don't bump that up, that they also preserve the same supersymmetry. So let's look at how that goes. To see what supersymmetry a gauge field configuration will preserve, we do exactly the same things we did for all the other fields. What we did there is we looked at the variation of the fermionic partner of the field, and after it gave 0 for our 4 supercharges of L n equals 1 theory. So what hypnotic theory actually is, it's essentially a coupling of Super-Yang-Mills theory in 10 dimensions for one of these gauge fields to this gravity center. So as well as our gauge fields, we have these fermionic gauginos, adjoint valued gauginos, fermions, and they have the variation. And it looks like this. I forget what I used to make that joke. And these are 10 dimensions, as it is. And in general, this is under one of our 16 component spinor transformations. This is how these things transform. Now, if we want this to preserve the same supersymmetry as our Calabi-Yau manifold, then what we need is that this variation is going to be acting on the preserved spinor by the manifold. The spinor that is preserved by the manifold is going to give 0. Okay. And just like we did with the H field and the derivative of the dilaton, we're going to take all the legs on the gauge field and its field strength to lie in the extra dimensions in Calabi-Yau. And that's just because if they had an index lying in 4-dimensional space, we'd break out assumption of maximum symmetry in 4D, right, in defined direction. So what we need is a gauge field configuration that's purely on the Calabi-Yau that satisfies this equation. Okay, so you can manipulate this a bit. So let's do that. So the Calabi-Yau metric is Kähler metric. So in particular, its inverse has vanishing 0, 2, and 2 0 piece. Okay. And that means that if you looked at the usual algebra of gamma matrices, right, normally the anti-commutator gamma matrices is metric, basically. So what this is telling you is that you can write this as 0, because that's 0, you can write this as 0. Nope. And the remaining commutator, which is the one with one bar and one half-bar index, is probably 2, yeah, 2, yeah, whatever that is. Okay, why is this a useful way to write gamma matrices? Well, up to normalization, this is a set of creation and annihilation operators.